we're going to start talking about the binomial probability distribution. It's going to be kind of a way of dealing with the number of successes when there's only two things that can happen in a fixed number of trials. So let's talk about flipping 4 coins. All the different things that can happen when you flip 4 coins. Well, flipping 4 coins or flipping the same coin 4 times doesn't matter. There's 2 things that can happen on the first flip, times 2 more that can happen on the second flip, and so on. So you're going to get 2 to the 4th, or 16 different possible events. And I've listed them out here for you, all the different possible events. Now what's true about this sample space here is that all the events are equally likely. So I can use that to help calculate some probabilities. On average, if you flip 2 coins, how many heads do you expect? Or if you flip 4 coins, or flip a coin 4 times, how many heads do you expect on average in that experiment? 2. Let's see if this distribution meets our expectations. If we're talking about the number of heads, how many ways are there to get 0 heads of all these 16 things that can happen in our sample space? 1. What's that? No, you don't have this one. Sorry. So there's only 1 out of 16. So 1 in 16 chance you're not going to get any heads.
Should we do this on sheets?
We can put that on sheets and just, you know what? Yeah, let me run through the distribution, and then we'll put this on sheets. Sure. So, how many ways are there to get 2, or actually 1 head out of all these 16 possibilities? And what you should concentrate on is just copying these down. You don't necessarily need to copy down the sample space. So, if I'm looking for exactly 1 head, that would be here, here, here. There should be 1 more. Yeah, right here. All right. So if you're looking for ways that you just get exactly 1 head, then there's 4 out of 16. Now for 2, well, 2 want exactly 2 heads. So let's see. Here, 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 here. Is that it? There. Bottom left. Thank you. So 6. 6 out of 16. And then last but not least, well, these are symmetric, so I'm just going to speed this up a little bit. 4 out of 16 and 1 out of 16. So if I wanted to find what happens on average, I could calculate the average the way we did in section 5.2, x times p of x, and sum it up. And what you're going to get is 2. The problem is, boy, it's a real pain to try and figure out this probability by looking at the sample space and counting. Especially because, if you get a head on the first flip, a tails, a head, a tails, that's essentially the same outcome as a tails, a head, a tails. So what we want is a better way to approach finding these probabilities rather than just listing out the sample space. And this is going to become a binomial random variable. So let me give you that definition. Binomial random variable. Binomial random variable is going to denote the number of successes in n trials where each trial has 2 equally likely outcomes. So the number of successes in n trials where each trial has two outcomes. Those are going to be success and failure. Now the pain that we ran into in this current example was calculating, how many different ways there were to come up with 2 heads and 2 tails for this experiment, or 1 head and 3 tails for this experiment. It's a counting thing, and it would be nice if we had a way to count those up. Fortunately, we do. So let me further describe binomial random variables in terms of their probability. P of x, where x is a binomial random variable. X is a binomial random variable. It's going to be given like this. It's going to be, no, I should probably give you a little bit more. Binomial random variable with n trials and x successes. And a little bit more notation. The probability of a success is going to be labeled P. Probability of a failure is going to be labeled Q. P plus Q has to equal 1. So there's a lot of notation here. Is there anything else I need? I think we're good. So the probability of getting X successes, and then the rest are going to be failures, out of this n trials is given by this. It's going to be n choose X times P to the X times Q to the n minus X. So here's your X successes. The rest of these Q are your failures. So what's that going to look like for our particular example just up above? So let's apply that to flipping 4 coins. Flip 4 coins. If you're going to flip a coin 4 times or flip 4 coins, that tells us n equals 4. If we're looking at a success as being flipping a head, what's the probability? So success equals flipping a head. Probability of success, what's the probability of tossing a head? Yeah, 0.5. Failure is going to be tossing a tail or flipping a tail. Probability of a failure is, again, 0.5. So that's going to be your Q. That's going to be your P. if I want to find the probability of getting exactly 2 heads, so x is the number of heads in 4 flips. Oops, 1p. X is the number of heads in 4 flips. Then this is a binomial random variable. So it's p of x equals 2 is going to be 4 choose 2 times 1/2 to the 2 power. I have 2 successes. Probability of each success is a 2. And the failures, the rest of these are failures. 4 minus 2, again to the 1/2 power. Now this 4 choose 2 stuff is really just counting up the different ways that this event can happen. You can get that off your calculator. 4 math over to probability. 4 math, then combinations. There's 6 different ways that this can be done. There's 6 different ways to choose 2 successes out of 4 trials. So it's going to be 6 times 1/4. 1/2 squared is going to be 1/4. 6 times 1/16 is 6/16. Whew. There's a lot of good news that's going to head your way slowly. But if you look back at our calculations, that number 6 is the number of different ways that you could get exactly 2 heads. We calculated that, we saw that up here in looking at our sample space. So that's what that's counting. And this is the probability of 2 successes times the probability of 2 failures. It gives us the overall probability of 6 over 16. That's what we got originally. All right, let's employ some technology here for ourselves. Let's go to Google Sheets. So the format of our command in Google Sheets, in fact, I think quite often it should tell you. No, it doesn't. All right, a lot of times it will tell you the format of the command. If you're ever in doubt, you can just Google it. So when you Google binomial distribution and Google Sheets, then you come up with this page. It tells you exactly how to use the command. So you're going to start out with number of successes, number of trials, probability of success, and then let's just put false for that last part here. So, so our Google Sheets command looks like this. Binomial distribution. Is it do I gotta spell it all the way out, or is it binom? Just binom. Yeah, binom dist. All right, so binom dist x, which is going to be your number of successes, n, which is the number of trials, and then p, which is going to be the probability of success, and then for now and in the near future, we're just going to type false here. I'm not really going to explain why. You can look at Google Sheets. What it'll do is it'll give you a cumulative distribution. We don't really want that just now. So let's see if we can't get Google Sheets to give us the same probability that we got in two other ways so far here, which is the 6/16, which has a decimal, I think is 0.3 something, 875? 6, yeah, 0.375. All right. So let's see if we can't get that same thing off of Google Sheets then. So we'll go back to a spreadsheet. Binomial distribution. I want 2 successes out of 4 trials. Probability of success in this case happens to be 0.5. And then the last thing I want to do is type false. There you go, 0.375. Let's try that again for a different combination of things. Same kind of thing. If we want binomial distribution, let's see if we can't find the probability of 1 success. So 1 out of 4 trials. Probability of success is 0.5. And again, false here. This time you should get 0.25 when you type that in. Yay. So in this way, we can avoid a lot of really ugly calculations. We can just jump right to the probabilities. Let's spend a little time getting familiar with let's see. Let's just spend a little time just getting familiar with binomial distributions themselves, trying to decide whether or not something actually represents a binomial random variable. And I'll help by giving you a little acronym that you can use when you're trying to decide if something's a binomial random variable. Does an experiment result in a binomial random variable? Well, what you're going to have to ask yourself is, does it fit? So see if it fits. Now, fits is a nice acronym because it's going to describe the 4 things you're going to have to test to decide whether or not something's a binomial random variable. So the F stands for fixed number of trials. So in our first case, it was, all right, are there 4 trials, 5 trials, etc.? In our example, there was 4 of them. The next thing is that the trials have to be independent. You can't have one trial or the outcome of one trial influencing the outcome of the next trial. So independence trials. There has to be exactly 2 outcomes. Success and failure. Probability of success is denoted with a P. Probability of failure is denoted with a Q. And just a quick FYI, Q equals 1 minus P, or P equals 1 minus Q. They're just mirror images of each other. Last but not least, the probability of success and failure has to remain the same throughout the trial. So, same probability of success / failure throughout the trial. Okay, let's look at a couple examples and try and decide if some of these result in a binomial random variable. The Y-sort method of gender selection developed by Genetics and IVF Institute is designed to increase the likelihood that a baby will be a boy. When 291 couples use the Y-sort method and give birth to 291 babies, the gender of the babies are recorded. So, if you're looking for boys, you're looking for girls, whichever the case may be, let's see if this is a binomial random variable. Is there a fixed number of trials? Yes, 291. Are the trials independent? Yeah. Baby of couple 1 and the baby of couple 2, their gender is going to be independent. So, independent. 2 outcomes? Boy or girl? Yes. And has that probability changed throughout the trial? Why? Well, now this method may have an effect, but that effect I think would be the same on all the couples, right? So the probability of success, while we might not know what that is, at least from this small little blurb of a problem, I think that probability would be the same for all the couples. So it's going to be some kind of average, statistical average. So yeah, problem number 6 is a binomial random variable. So the number of kids that you would have, boys or girls, depending on which one you want to call your success, that's going to be a binomial random variable. Let's take a look at problem number 8. Veggie survey. An Idaho Potato Commission survey of 1,000 adults. Subjects are asked to select their favorite vegetables, and responses of potatoes, corn, broccoli, tomatoes, and other were recorded. So, fixed number of trials? Yep. Independent. Yeah, what somebody likes is independent of somebody else. 2 outcomes? No. There's more than 2 outcomes, so we can stop there. It's not a binomial random variable. So we'll just stop. Let's look at problem number 10. And we'll assume that these are United States senators. 10 different senators are randomly selected without replacement, and the number of terms they have served are recorded. So, fixed number of trials? Yes. Independent? No. If you've got a small population and you're sampling without replacement, then it's not going to be independent events. So, no. And the 2 outcomes fails there too, right? I mean, you could have a lot of different number of terms that are served depending on what senator you happen to find. So we could have stopped here. This is not going to be a binomial random variable. Let's practice a couple that are. We'll start with problem number 16. Now we're not going to use the table in this case because we're going to use Google Sheets. Well, let's take a look at the experiment. Assume that random guesses are made for 5 multiple choice questions on an ACT test, so that there are n equals 5 trials, each with a probability of success, that is correct, given by p equals 0.20. Use the binomial table to find the probability indicated for the number of correct answers. We're not actually going to have to go there. Let's calculate it for ourselves. So n equals 6. Probability of success is 0.2. And actually, we're going to go a little bit farther. We're going to come up with a whole table of values. Let's come up with the entire distribution. So we've got 5 guesses. So the number of successes that you could have is anywhere between 0 and 5. You could get them all right, you could get them all wrong. Just depends on how lucky you are. So let's type in the numbers 0 through 5, and then find the associated probabilities of each of these. So equals binomial disp the number of successes. Let me just click this column A. That way I can copy my command from this first cell all the way down to the next ones and have it fill out my probability distribution. So I typed in binomial distribution, and then I clicked column A, which has a 0 in it right now, comma, n, which comes next. N is the number of trials. I think I wrote a 6 by accident. I should have written a 5 on my paper, so let me just correct that. There should be a 5 here. Probability of success comes next, 0.2, and then false. So it's about a 1/3 chance you're not going to get any right if you make 5 guesses on the ACT. Basically, I wouldn't recommend it as a strategy. Now let's copy this and paste it down to the rest of these. Okay. So that's our probability distribution. Let's see how well Google Sheets did in calculating these. Essentially, what do I expect here if I add all these up? 1. You expect 1 because it should be a probability distribution. Great. So now we've got everything. Let's turn back to the book and answer some questions. It says find the probability that the number of correct guesses is at least 3. So if I want to find the probability that the number of correct guesses is at least 3, what events satisfy at least 3? Say again? Yeah, 3, 4, and 5. So looking back here, oops, not there. There. So that should be a 5. Probability of at least 3 equals probability of x equal 3, or x equal 4, or x equals 5. Fortunately for us, these are mutually exclusive events. So all we have to do is add up those 3 probabilities, and that's even easier now that we've got Google Sheets. So I'm going to go here, equals sum, and let's select those 3 events. Sum of those probabilities. Wow, that's pretty nice and quick. So a little bit less than a 6% chance of coming up with at least 3 correct guesses. 0.059 or 792. How many of you were able to get this column here for the distribution? All right, good, thank you. Let's try some more here. Problem number 18. Find the probability that the number of correct guesses is fewer than 3. Now here's a good question for you. If I want to find the probability of fewer than 3 correct guesses, so let's take a look at that. Probability of fewer than 3. Does that actually count 3? No. Anything under 3. So the ones we should be adding up are 0 or 1 or 2. And again, what's nice for us is that you can just do that. I mean, you just add up x equals 0 plus probability that x equals 1 plus probability that x equals 2. We've already got those on Google Sheets. I'll copy it down here in a second. We can split that up because these probabilities are, or these events are disjoint. So let me just clear this out. This time I want the sum of 0 through 2. Oops. Let's try it again. 0 through 2. That makes sense. In fact, in retrospect, what's another way I could have done this problem? Yeah, 1 minus our result from problem 16, right? So, all right. Missed a chance to capitalize on the complementation rule, but that's all right. So in case you're curious, this would be the brute force approach, although I'm hoping that we can avoid a lot of that hand computation. Let's try problem number 22. An experiment assumed when blood donors are randomly selected, 45% of them have blood that is in group O, based on data from the Greater New York Blood Program. If the number of blood donors is n equals 16, find the probability that the number with group O blood is 6. So go ahead and give that one a shot. And I'll walk around and try and help out. If you're running into some problems, please let me know. Once again, the command is binom dist x for your number of successes, n for the number of trials, p for the probability of success, and then false. So, number of successes, number of trials, probability of success,
where here the probability is 0.45.
I put in the formula on that.
Do they not have to type out all those 0 through 16? You wouldn't even have to do that. You could pick any cell.
Six successes. With the probability of success.
Yeah, click any cell, like other than that one. Like you already have all those numbers. You don't even need those for this one.
Okay, which cells?
You can go to a blank cell. Just go to a blank cell.
All right. Doing all right with this calculation?
So do equals. Oh, you went back to.
Okay. So in this particular case, n was 16, x was 6, and probability of success is 0.45. So I'll just type that in here. Equals binomial distribution. There we go. Fill it out. And then we had 6, comma 16, comma 0.45, comma false. So a little bit over 16, 17% almost. So not too bad. Certainly not an unheard of result. A few of you went a little bit above and beyond what we might have needed to have done. So let me address that and just give you a little bit more practice in calculating the entire distribution. So if I want to go all the way down to 15, oops, rats. It's supposed to equals that plus 1. All right, so actually I got to go down to 16. One more. So if I wanted the actual probability distribution, if I wanted everything here, then let's clear this out. Move columns left. Wasn't what I wanted. All right, I guess it was. Close enough. Delete columns A and B. There. So what I could do to get the entire distribution is do equals binomial distribution, and then I want my number of successes is going to be this first variable here. It's going to come from this column. So that's going to be a variable, comma, 16 was our n. Probability of success was 0.45, and then false. So pretty small the chance you would get 0 people with that type O blood. Let's copy this all the way down to 16. And again, a really small chance you get all 16 with type O blood. To double check this, you could sum this up. And you get 1, which you should. This is a probability distribution. What's nice is that you didn't even get any rounding error in this one. Another nice thing is that I could ask you questions from within this. If you had this entire table, I could ask you, for instance, well, what's the probability of getting between 4 and 12 people that have this type of blood? And then it'd just be a matter of summing up these values, which you can do really, really quickly on an Excel spreadsheet or Google Sheets. So a lot of advantages, I think, in doing it this way. And of course, the ultimate advantage is not having to actually use the formula, which is kind of nice. So yeah, a few nods there, like, oh, yeah, not really happy with the formulas. Are you comfortable getting some of these values out of Google Sheets? All right, let me give you some homework. So let's try 1 through 31 in homework. that'll do it.